Hello everyone. Today I'm gonna talk about the conference paper that I have reviewed, and it is about fiber wireless and optical wireless communications by using high-speed photonic devices. And here is the content of my presentation: introduction, overview of key contributions, fiber wireless communication. Then we're going to talk about optical wireless. Then we compare and contrast the strengths and weaknesses of the two systems. And finally, we will be in the conclusion. As an introduction, this paper is authored by Toshimasa Umezawa and his colleagues, and they introduce groundbreaking technologies by combining the photonics and wireless communication systems. Because of these innovations, they can address to the challenges like data capacity, latency, and system integration for the next generation networks such as 5G and 6G and beyond. As an overview of key contributions, the experiments mainly focus on the two-way approach. The first way is to use fiber connection, and the second, they use laser beam in free space. So fiber wireless communication, they want to achieve the data rate by exceeding 20 gigabit per second when they use 100 gigahertz photodetector. And the next, optical wireless communication, they want to achieve the data rate above 100 gigabit per second by the use of two-dimensional photodetector array, 2D PDA, and wavelength division multiplexing. So for fiber wireless communication, there is an integrated component which is a combination of UTC, PD, and amplifier. UTC PD means Uni-Traveling Carrier Photodetector, and the amplifier they use is PHEMT. It's pseudo-morphic high electron mobility transistor, 90 GHz, is used in this experiment. Here is the picture that shows the integrated photoreceiver, and the input is optical signal and the output is radio frequency signal. The optical signal has a range of 90 to 100 gigahertz for this component. And this is the experiment they carried out by using the above integrated photoreceiver. The input signal is generated from this side, and that signal is traveled through all these processes until it reaches to the photodetector. And the signal is transmitted via wirelessly for a certain amount of distance, and the signal is received at the receiver side and demodulated and amplified, and finally the data is monitored by the use of a real-time oscilloscope. So the input signal is an optical signal. They use two-tone, and one of this signal is modulated by use of 16 QAM, and it has the speed of 21.6 gigabit per second. And then this modulated signal and the unmodulated signal is combined behind the optical coupler, and the combined signal is then transmitted through the fiber connections until up to 10 kilometers. The optical signal is attenuated over such a distance because of the fiber loss. So we need to boost the signal strength by the use of this fiber amplifier. EDFA, this is the meaning of EDFA. PD stands for photodetector, and we use UTC PD here. Okay, and yeah, the signal is then traveled through and it is reached to the photodetector. And LO is another terms of local oscillator. And in this experiment, this can be seen as a demodulator. RTO is real-time oscilloscope. And this is the simulation result of the fiber wireless communication system. Here we can see that the value of uh, error vector magnitude in percentage is quite small when you compare with the received power. So the lower the magnitude of the error vector, the better the system for high-speed communication. And in this experiment, received power plus 12 dBm to plus 14 dBm is achieved. So it can be used for middle range distant millimeter wave wireless communication. So for the second part of the experiment, it is optical wireless communication. They use 2D PDA. It's a two-dimensional photodetector array, not a single photodetector. They use 6 multiply 6 photodetector pixels. Here is the picture of their design. According to their design, the detection area become larger, and it has 250 micrometer times 250 micrometer area. In this wireless communication, this is the process. Input signal is travel through the free space and then it receives at the 2D PDA, and the signal is monitored and shown in the real-time oscilloscope. So as a source, they use a free space optical FSO beam, and they use wavelength division multiplexing. So in here for WDM means they divide the FSO beam into 4 different wavelengths, and each has a 25 gate baud rate. So it's totally 4 times 25 means 100 gate baud rate. Baud rate and data rate has a relationship. Like baud rate is how many symbol is sent per second, and the data rate is how many bits are sent per symbol. So if you want to change this baud rate into data rate, yeah, you can change it, and it's this here is the same. Because if you calculate, you can you will have the same answer. So if you want data rate, you need to change from baud rate. And 25 gate baud rate means 25 gate symbol per second. And this, according to the WDM, 4 bits are sent per symbol. So if you change the baud rate to data rate, you will get 100 gigabit per second. So at the receiving side, there is an optical filter. Its functions is to separate the incoming FSO beam into different wavelengths. And these four channels are transmitted to 2D PDA and then monitor in a real-time oscilloscope. And this is the result of the optical wireless communication. And here you can see that BER, bit error rate, is quite low for great for receive power. I mean, the higher the receive power, the lower the BER rate. So it means that it indicates that the stronger signals result in fewer errors. Those signals become stronger and the errors become fewer. So it is quite good for high-speed communication. So if I compare and contrast between these two systems, fiber wireless communication and optical wireless communication, there are strengths and weaknesses. So they can apply the integration of photonic devices in wireless system. That's one strength. Um, and they can do some kind of minor modification in the whole system for larger scale deployments. And they can also address to the challenge for signal alignment and noises because they use 2D PDA. It's not a single photodetector but a combination of 36 photodetector. So it has a larger uh, detection area. So it can challenge to the signal alignment. But everything has drawback, and as you can see, uh, their communication distance is quite limited to only a few distance. So it is limited to outdoor applications. And their experiments are not focused on energy efficiency, and their short range limitations restrict broader usability. So as a conclusion, fiber wireless communication. And in their experiment, they achieve data rates above 20 gigabit per second for millimeter wave fiber wireless communication. And that data rate is a constant on fiber cable until up to 10 kilometer. And over such distance, it is needed to be amplified because of the fiber loss. And in this experiment, they achieve uh, that data rate 20 gigabit per second in the wireless channel for 4 meter. It's quite small. So in order to enhance its communication distance and performance, they propose to use MIMO, uh, that can increase the signal to noise ratio. Because the higher the signal to noise ratio, the lower the bit error rate, and the fewer the error beta magnitude. So by increasing the SNR value, we can achieve longer distance of communication. And for the optical wireless communication, they demonstrate a 100 gigabit per second total data rate by using 4-channel wave division multiplexing, and each of channel has a 20 gig baud rate, and also alignment tolerance is quite high because they use two-dimensional photodetector array, and because of these structure and characteristic, bit error rate result in very satisfying level. So, and 2G PDA systems is ideal for short-range indoor communications, such as high-speed data links in data centers or IoT applications. So, both communication system has on limited range of communication distance, and here space diversity techniques is recommended to use for further improvements in optical wireless communication. And this technique has the same contribution to the signal-to-noise ratio. It can increase, so by this means, it can extend the communication distance. So that's it. This is the end of my presentation. Thank you. So if you have any questions or anything you want to know, please leave comments down below, and I will reply you as soon as possible. Thank you for your time and patience. Good luck.